Okay guys, we're going to be working on our graphing motion notes, for regular physics. We're going to be a little bit of converting too by the time we get done, but these notes, it's late. I'm going to try to push through them, so just bear with me. Okay, so we got graphing motion. This is the first thing we're going to do when we talk about graphing motion is we want to talk about slope. So slope is the steepness of a line, and we talk about positive, negative, or zero slope. If you feel good on this, you can kind of skip ahead the video until the next slide, but I'm going to talk about this a little bit in depth. So I like to think of positive slope as if like there's a stick person here, and they're walking along this line. What direction do they have to look? And they have to look up, and they have to be in a positive mood when they're looking up. The next example then would be is if a person's walking on this line and they're looking down. You know, if they're a negative person, they have a negative slope. And then there's always that one student who walks into class, never happy, never sad, just there. I would say they are a zero slope. We're really not going to use undefined too often just because it breaks the laws of physics. So we really just don't really talk about it too much. So I really need you to understand what a positive, negative, and a zero slopes are. Excuse me. All right. So let's look at the slope of a position versus time graph. So if I was in your shoes, I would write this as a displacement, because position and displacement are the same thing, versus time graph, meaning t. Okay? Now, before we get there, let's unpack what this is. So, slope is the letter M and is often denoted as rise over run. Or, that's kind of like a middle school definition of slope. What we can also talk about is the change in y over the change in x. How quickly does it go up or down? And how quickly does it go over or to the left? So when you're looking at slope is, what is your change in your y variable versus the change in your x variable? So for us, our y variable is displacement, and our x is t. So if we're looking at this, actually, our change in y is actually change in displacement over change in time. Well, we learned last week that that is velocity. Velocity is displacement over time. So what do we do with this? How can we use this? Well, looking overall at this graph, we can see that the first 5 seconds here, okay, is a positive slope. It's going to be some positive here. So velocity is going to be positive. And then for the second set of 5 seconds, that's a little bit of a tongue twizzler, we see velocity is going to be equal to 0 because it has a 0 slope. So the slope of a distance versus time graph, the slope is equal to velocity. Okay? Regardless if it's up or if it's down, if it's flat, doesn't really matter, but the slope is equal to velocity. Now we should be able to find this first segment of velocity here. I'm going to say we're going to look at our rise. So how far up did I go? I went up 25 meters, and my time, my displacement here, is 5 seconds. So velocity equals 5 meters per second. Okay? We know it's positive because we're going up, and we also found it algebraically of it going up as well. Okay? So what I want you to do now is I want you to try this on your own. What we're going to do is I'm going to label these. We're going to say this is velocity 1. This is velocity 2. Let's try this again. Velocity 2. We're going to call this big line velocity 3. And this last one velocity 4. Okay? I want you to pause on the video, and I want you to find these velocities out on your own. Okay? Describe what they're doing quantitatively, meaning with numbers, find the speeds or the velocities. And then qualitatively, what direction is the object going? Okay? So go ahead and pause the video and try these out on your own. Okay, so what is happening for this first velocity? Make sure my board's straight. There we go. Is that for velocity of 1, we notice that the slope is positive, which means this for the first one is going to the right. So that's describing it qualitatively. As we see, the slope is positive over here. It's going up, and which means our object's going to the right. I guess it could be going up too. Okay, but it's going in the right direction. What else could we do? Well, we could also calculate the velocity. So the velocity of this first one would be, we went up, our rise is 60 meters, and our run is 15 seconds. Or sorry, nope, I'll take that back. 10 seconds. There we go. 10 seconds. So our velocity here is going to be 6 meters per second for the first velocity. Okay, let's go blue now. Let's go blue for velocity 2. Well, velocity 2, the slope is equal to 0, which means it's not moving. Pretty easy there, which means the velocity here for 2 is 0 meters per second. Because the slope here is flat across, which means it is 0. Okay. Up next, let's do velocity 3. Now for velocity 3, you could do any segments along that line. I'm going to do the whole thing. So if we look at the slope is negative. So what does that mean? Well, that means the object is moving to the left or down. To find that slope, it would be rise over run. Our rise is 60 plus another 40 down. So it's negative 100 meters across. Time equals 15 to time equals 40. That's 25 seconds. So a negative 100 divided by 25, that'll be negative 4 meters per second. So does it make sense that it's negative because it's going down, which means the object's going to be traveling to the left? I don't know which way is going to show up on the video. I don't know if it flips or not. I'm going to say that's left. Okay. All right. And the last one. Oh, we'll put velocity 4. Our slope is positive, which means we're going to go to the right. And our velocity 4 here is going to be, our rise looks like it's going to be 40 meters over 15 seconds. And I believe it's going to get us an answer of 2.6 meters per second, or 2.7 would be more rounded. Okay. Sweet. So we've looked at position versus time, or displacement versus time graphs. And that slope will tell us the velocity. What if we change what we got going on here? And instead of a position versus time graph, we do a velocity versus time graph. So this is different than the graphs we were just doing. See how displacement is along your y? Here we now have velocity. Okay. We are going to X and A. This first chunk right here, we're going to ignore acceleration for now and just play with velocity and displacement. Okay. When you look at a velocity versus time graph, the area under the line, so this is my line right here, tells you displacement. And I'm going to show you why that is here in a second. So in blue, there's our area under the line. Let's see if I can draw that red line a little bit better. Let's make it just a little bit thicker. See if I can follow along. Okay, so there's our red line. The area under the red line is displacement. But why? Well, let's look at this. The area of this shape right here is a triangle, which is 1/2 base times height. Well, area equals 1/2. What is the unit of my base here? And that's time. What's the unit of my height? And that's velocity. So what I'm going to do here is I'm going to do a little bit of math magic. What happens if you take velocity times time? What does that give you? Well, here's the velocity formula. If we rearrange this a little bit, we get displacement equals velocity times time. Velocity and time, velocity and time. So, displacement is your area under the line. So, anytime we're looking at a graph, we have a velocity versus time graph. The area under the line tells you displacement. Okay, so let's do that for this one right here. The area under the line is 1/2. Our base is 5 seconds. And our velocity, our max velocity is 20. Our height is 20 meters per second. Well, what does the units in here do? So seconds cancels out seconds. And so I'm left with 1/2 times 20, which is 10. 10 times 5 is 50. And what's my final unit? That is meters. Okay. So in a displacement versus time graph, the slope tells us velocity. In a velocity versus time graph, the area under the line tells us displacement, or how far you went. So overall, this object went 50 meters to the right. Yeah, that should be the right video. Okay? All right, here's what I want you to do. To look at this question and try to find the area under the line and find out what is your final displacement at t equals 5 seconds. Okay? So go ahead and hit pause on the video, try this on your own, see if we get there. If you have no clue, just wait a second, we'll do it together. All right. So, I notice that there is a triangle. Let's do it blue. We'll see why in a second. Okay. All right. Let's do this first one, blue. If I take this weird shape, I can chop it up into a couple different shapes. We have a triangle, we have a rectangle, and we have another triangle. So can we find the area of these 3 shapes? Yes. So the area in total under the line is going to be this first triangle right here, plus this rectangle right here, plus that triangle right there. So we're going to call this, area 1, we'll call this area 2, we'll call this area 3. So the area under the line in total will be area 1 plus area 2 plus area 3. Okay? Now, let's look at my line right here. Notice how it goes down and it is below 0, which means my velocity is negative. So if it's above 0, your displacement's positive. If it's below 0, your displacement is negative. So area total is going to be A1 plus A2 plus A3 plus this A4, and we'll call this the whole one A4. And you're like, but wait a second, you just said it was negative. Watch the math magic. So we got area total. Our first shape right here is a triangle, which is 1/2 base times height. And we'll call that all of shape 1. Area 2 is a rectangle, so we'll do that as base 2, height 2. Area 3 is going to be another triangle, so that's 1/2 base 3, height 3. And then the last one is going to be another triangle. However, 1/2 base, which is your time, and your height is going to be a negative number. So let's go and plug some of these numbers in. We got 1/2. Base 1 is, that should be 0.5 seconds. Times height, which is 3. For the sake of space, I'm not going to put the units in there. Okay. Plus base times height. This is 1.5 times 3. Plus 1/2 base 3 is going to be 2 to 3. So that's going to be 1 with a height of 3. And then the last one's going to be 1/2 with your base of 2 seconds, but your height of -3 since it's going downwards. Okay, that's where that negative actually comes in at. This is a big thing to figure out, that negative. Okay. All right, what's our first one going to be? Area total. What's 1/2 0.5 times 3? Did I do that one right? Yeah, 0.75. Plus 1/2 times 3, that's 4.5. Plus 1/2 times 3 times 1, that's 1.5. Plus, well, what's 1/2 times 2, which is 1, -3. Times -3 is -3. Add all these together, what do we get? This is 6 minus 3. So the area total under the line is going to be 3.75 centimeters, which is your displacement. It tells you how far away you are from where you started. So overall, what did this object do? It went in the positive direction, and then after a while, it then stopped and then started to go in the negative direction, and then comes to a stop. But I didn't draw that very well. Let's try that again. So the object started at 0, wasn't doing anything. It sped up, it increased its velocity to when it was going at constant velocity for a while, slows down, and then comes to a stop. What did it then do? Well, since it's going negative, went in the negative direction, slowed down, stopped, and at some point it had a positive displacement. So we'll do displacement equals 3.75. Where did I get centimeters from? The graph. The graph says our units of displacement and distance is centimeters. Okay, this is a tough example. If you need help, absolutely ask me questions, and I'd love to help you figure it out. Okay? What we're going to do now is we're going to change gears just a little bit and talk about conversions. When we do assignments, you have to deal with big numbers, you have to deal with small numbers, you have to be able to convert. The 3 types of conversions we're going to do, beyond things you already know, like 60 seconds equals 1 minute, are these 3 right here. So go ahead and hit pause on the video, write those 3 down, because we're going to be using them a lot in this class. Okay, so What is a conversion? If I tell you the number 12, 12 is the same thing as a dozen. So if say 1 dozen eggs, it means you have 12 eggs. What about a kilometer? Well, the word kilo, or the prefix kilo, actually means 1,000. So a kilometer means 1,000 meters. So 1 kilometer, or what I often write it is in this class, is 1 kilometer equals 1,000 meters. If I were to take my meter stick and put it in a blender and chop it up into 100 equal pieces, that would be 1 centimeter. And then if I were even to take my meter stick and blend it even more, this would be millimeters. So let's put that right. There we go. Okay. We're going to use these numbers here in a second to convert some speeds and velocities. Okay. So let's try this out for me. Convert meters per hour to centimeters per hour. Let's do it. So we have 3 meters per hour, and we want to convert it to where we get centimeters on top and hours on bottom. Okay. If we were to wander into a math class and this fraction was on the board, or this fraction multiplication was on the board, I really hope you could do and know that these 7s would cancel out. And then it would just be 3 over 1. We're going to do the same thing, but instead with numbers, we're going to do it with units. So if I want this meters to cancel out, because I want to turn it into centimeters, I have to put meters on bottom. Has to. Well, if I'm going from meters, what am I going to? Centimeters, because we want centimeters to be on top. Okay? Well, what about hours? Well, hours and hours stay there. We're actually not going to touch it. So how do we then convert from centimeters to meters? Well, for every 100 centimeters equals 1 meter. We just wrote that down. Oh, let's try that. There you go. 100 centimeters equals 1 meter. Okay, so let's look at it. For every 100 centimeters, we have 1 meter. Meters cancel out the same way that the 7s cancel out over here. Units also cancel out, and what are we left with? We're left with centimeters on top and hours on bottom. What's 3 times 100? 300? That's it. So the answer is 300 centimeters per hour. Okay. That one isn't too bad. We're running into a little bit of a problem with the second one, though, and this third one, is we need to convert both the top and the bottom, or the numerator and the denominator. So let's do that. We have 1,516 meters per minute, and we want to get to kilometers per hour. So let's try this out. Okay, I'm going to erase this just a little bit, and I'm going to draw this equal sign right here. Okay. If I want to go from meters to kilometers, we're going to have to get the meters to cancel out. And we're going to go 2 kilometers. So back to what we did earlier. How many kilometers is in a meter? How many meters in a kilometer? So it's going to be 1,000 meters is 1 kilometer. Okay. We are almost done here, though, because we got meters to cancel out, but not. We still have minutes here. We want minutes to cancel out. So if minutes are on bottom here, what do we do to get them to cancel out? We're going to put them on top. If we're going from minutes to hours, we're going to put minutes on top, hours on bottom, and in every 1 hour, you have 60 minutes. So run on my calculator, we're going to punch this in. I'm going to type in 1516 divided by 1,000 times 60, 90.96 kilometers per hour. So 90.96 kilometers per hour. Okay. All right. Here's what I want you to try. This third example on your own. So go ahead and hit pause on the video. See if you can do this by yourself. Okay. All right. I'm going to see if I can do this quick. So 7,200 millimeters per second, 2 kilometers per hour. Well, millimeters is going to go on bottom, meters is going to go on top. 1,000 millimeters is 1 meter. So millimeters cancel out. Now I have meters per second. I'm still not there yet though, and I want to have kilometers. So meters on bottom, kilometers on top. For every 1 kilometer, there's 1,000 meters. Meters cancel. So now I'm at kilometers per second. That's like a really weird speed unit. So we're going to want seconds to cancel. We've got seconds on top, minutes on bottom, and then minutes on top, hours on bottom. And that gets us from seconds to hours. Well, how many seconds are in a minute? And how many minutes are in an hour? So what does that get us to a final answer of? Survey says times 60 times 60, 25.92 kilometers per hour. Okay. All right, guys, we did quite a bit with these notes. If you need help, absolutely feel free to reach out, and I'd love to help you figure it out. You guys take care, and I will see you on the next video or in class or doing whatever shenanigans and science stuff you find yourselves getting into. Take care. I'll see you later.